Reduction of carbonyls is one of the ways in order to prepare alcohols. Reduction is the opposite of oxidation, and reduction means adding hydrogen. So oxidation means taking away hydrogens. Reduction means adding hydrogens in there. Your starting material here is always the carbonyl, and you are adding hydrogens to the carbonyls. You are adding a hydrogen to the carbon and the hydrogen to the oxygen. So you're going to end up with these types of reactions in there, forming a hydrogen on the carbon and the hydrogen on the oxygen. So you're going to end up getting your alcohol in this case. The alcohol that you're going to form is either a primary or a secondary alcohol. And the type of the alcohol that you're going to form depends on the type of the carbonyl that you are going to start with. There are three types of carbonyls that we're going to start with. We're going to start either with an aldehyde, or we are going to start with a ketone, or we're going to start with the ester. Esters are the same as acidic chloride, so let's go ahead and add a fourth type, which is the acidic chloride. They go with the same reaction. The general formula of the ester is an RC double bond O, OR prime. And the general formula for the acidic chloride is an RC double bond O and a chlorine. Okay, so you can start with either one of those carbonyls, and your product is going to be a primary or a secondary alcohol. Now, reducing agents are classified into strong and weak reducing agents. The strong reducing agents, they work with all types of carbonyls. The weak reducing agent only works with aldehydes and ketones. So let's have an example of the strong and the weak. So the strong reducing agents, this is lithium aluminum hydride. This is the Lewis structure for the lithium aluminum hydride. Lithium aluminum hydride is an aluminum that is bonded to 4 hydrogens. Each of these hydrogens is a negative charge because the aluminum is a 3 positive. So the total charge for the structure is negative, that is balanced with the lithium, which is positive in there. So this is why the type of bond between the lithium and the aluminum is an ionic bond. Now, in order to represent the lithium aluminum hydride, now all of these bonds are covalent, by the way. Okay, it's only the bond between the lithium and the aluminum is the ionic bond. But just to make it easy to represent the hydride whenever it's released, because lithium aluminum hydride releases a hydrogen. That hydrogen is a negative charge and it's a lone pair. So always represent the lithium aluminum hydride by an H minus. This type of reducing agent is a strong reducing agent. Remember, reducing agents, they add hydrogens. So in order to be called a reducing agent, it needs to have a hydrogen. And here this one has 4 hydrogens in there. So it's considered to be a strong reducing agent, especially because the hydrides are coupled with aluminum. And aluminum is a strong metal. So these hydrides, these are strong nucleophiles and they are strong bases. They are strong nucleophiles in case there is no acidic hydrogen in the solution. However, if there is an acidic hydrogen, then they're going to behave as a base and they're going to take the acidic hydrogen every single time. So pay attention to that. H minus has a double role as a nucleophile and as a base. Always in organic reactions, acid-base reactions are always the priority. So if there's an acidic hydrogen, then the hydride is going to act as a base immediately. It's not going to act as a nucleophile. It's going to act as a nucleophile only if there's no acidic hydrogen. The other type of reducing agent is sodium borohydride, NaBH4. This is a weak reducing agent. The reason why, even though boron still has 4 hydrides coupled to it, The aluminum is a strong metal. So the hydride that is coupled to the aluminum is a strong hydride compared to the hydride that is coupled to boron. Borohydride releases a hydride still, but this hydride is going to be less reactive than the hydride that is released from the aluminum hydride. So this is why this one only reacts with aldehydes and ketones. If you start with an aldehyde, then your reaction is going to proceed and your product is going to be forming a primary alcohol. If you start with a ketone, then your product is going to be a secondary alcohol. Let's have an example. So sodium borohydride always requires a solvent with it. And because we have sodium, we want to stay away from water. So this is why the best solvent that has a hydrogen is methanol. You can use any solvent that has a hydrogen, not necessarily methanol, but we want to stay away from the water because of the sodium. Sodium reacts violently with water. So sodium borohydride is going to release an H minus. You are responsible for the mechanism of these reactions. To make it easy, represent the sodium borohydride by an H minus in there. Now, if you look at the carbonyls, from the beginning over there, carbonyls are polar. So they are going to produce a direction of polarization towards the oxygen. This makes the carbonyl to be a partial positive charge and the oxygen to be a partial negative charge. Now, since the carbonyl is a partial positive charge, this is my electrophilic site. So any nucleophile that is found in the solution, this is going to come and attack the carbon. Please apply the rules because the rules are always the same. If you have a nucleophile in the solution, the nucleophile is always going to attack the electrophile. So you have to know how to select your electrophile. And then if you're forming a bond between the nucleophile and the electrophile, every time you make a bond, you break a bond. So you have to break the carbonyl and add the electrons or the lone pairs to the oxygen. This is why the reaction proceeds by two steps in there, because the second step, you need to have a solvent with hydrogen just to protonate the oxygen. So you start with your hydride. Hydride reacts with the electrophilic site. And notice that I labeled this carbon partial positive in there. This is called the mechanism of the reaction. So the mechanism is not just drawing the product. The mechanism is showing how the nucleophile is attacking the electrophile, how the bonds are formed, and how the bonds are being broken. So the double bond is going to open up, add electrons to the oxygen. So now the oxygen is going to end up having 3 lone pairs in this case. So this is the new lone pair in here. And this is the hydrogen that I added. Again, whenever you're working with reactions, your product has to be neutral. It cannot be negative charge or positive charge. So this is why you would need a solvent in the reaction that has a hydrogen. This step is called a protonation step, which is an acid-base reaction. Always acid-base reactions are the last step in the reaction just to ensure that your product is neutral. So this is going to act as a base. This is the acidic hydrogen. So the base is going to come and take the acidic hydrogen. OCH3 is going to leave, and you're going to end up getting your product in this case, which is the primary alcohol. That OCH3 that is going to leave, of course, this is going to be coupled with sodium, because sodium is the positive charge and you allow the OCH3 to leave in there from the solvent. So that is going to be coupled with the sodium. You don't have to mention this, but everything that leaves is going to stay in the solution. But we only care about the organic product though. So what I did over here is simply I removed the pi bond and I added a hydrogen to this carbon and a hydrogen to this oxygen. And you're going to end up getting your primary alcohol. So aldehydes always form primary alcohols. Ketones, they form secondary alcohols. Now with lithium aluminum hydride, here's the thing. With sodium borohydride and the solvent, This happens simultaneously, so it's not a two-step reaction. You mix the sodium borohydride with the solvent, and then you add everything together to the aldehyde. But with the lithium aluminum hydride, no. With the lithium aluminum hydride, you start first by introducing your lithium aluminum hydride, and then you introduce the water. So this is why it's two steps. It's a two separate step reaction. You do step one, and then you form the product of step one, and then you do the step two. Okay. So with the lithium aluminum hydride, again, it releases H minus. For simplicity, just go ahead and represent it as an H minus in there. Lithium aluminum hydride is very reactive. It's going to keep reacting as long as there is a carbonyl in the solution. So every time there's a carbonyl, it's going to go ahead and react. Whether it's in excess or it's not in excess, it's going to react. So the hydride is going to attack the carbon, form a negative charge, and now in the next step, I'm protonating. So this is going to protonate, and OH is going to leave. Now, the thing here, we all know that OH is a very bad leaving group. Yes, but not for the protonation step. Because when the OH leaves, you are having your lithium in the solution. And lithium is positive. So lithium is going to balance the OH, and you're going to have the lithium hydroxide. So in this case, OH is not a bad leaving group because when it leaves, it's having a metal that is balancing it out. So your product here is going to be a secondary alcohol. So what I did here is I added a hydrogen to this carbon and the hydrogen to this oxygen in there. This is what I did, and I removed the double bond. So primary alcohols are formed from aldehydes, secondary alcohols are formed from ketones. It doesn't matter if you're using aldehydes and ketones. You can use mild oxidizing, mild reducing agents or strong reducing agents, and you can form your product in there. What matters now is with esters and acid chlorides. Esters and acid chlorides, they have no reaction with sodium borohydride, with mild oxidizing agents. They only have a reaction with lithium aluminum hydride. So only work with lithium aluminum hydride. They don't work with the sodium borohydride. The reason why, because lithium aluminum hydride is way more reactive than the sodium borohydride. And throughout the process of the reaction, of the reduction of the esters and acid chlorides, you're going to end up forming a leaving group and forming a carbonyl again. So this is why you are required to use this guy again. This is very reactive, so it can be used as long as there is a carbonyl. But this one is not reactive, so this is why it will not work in these types of reactions. Let's have an example. You might see the word excess in there. Sometimes we don't mention it. So excess is not a must for the lithium aluminum hydride to react more than once, because by definition, lithium aluminum hydride is very reactive. It's going to keep reacting as long as there is a carbonyl in the solution. If there is a carbonyl, it's going to keep reacting once and twice and 3 times until it gets rid of all the carbonyls. Once it gets rid of all the carbonyls, then you are going to protonate. So the first step over here is the hydride. Lithium aluminum hydride will release a hydride. It's going to attack the partial positive charged carbon. And then the oxygen is going to be a negative charge. The one's going to open, form a negative charge on the oxygen. Okay. Now, once you form a negative charge on the oxygen, this is the difference between this and aldehydes and ketones. With aldehydes and ketones, you didn't have a leaving group. But always with esters, you have a leaving group. And the leaving group is the OR. Now, your medium that you are working with here, for the lithium aluminum hydride, this is not an acid. This is an H minus. And an H minus is a base. So it is a basic medium. By definition, oxygen is a good leaving group in a form of a lone pair if you are working with a basic medium. So this oxygen here is going to leave. How it's going to leave? By resonance. So the lone pairs are going to form a double bond, and this guy is going to leave. So you are back to your carbonyl again. I said from the beginning that the lithium aluminum hydride will keep reacting as long as you have a carbonyl. It will stop reacting once you stop having a carbonyl. So here, the lithium aluminum hydride will react again. I mean by reacting again, another mole of the lithium aluminum hydride will come and attack. It's going to attack the carbon of the carbonyl, form a negative charge on the oxygen. You're going to end up having the negative charge on the oxygen there. There is no other leaving group to leave, so that's it. Now we're going to go to the next step of the reaction where we need to protonate the oxygen in there by simply having an acid-base reaction. The OH is going to leave and you're going to end up getting a primary alcohol. So esters with lithium aluminum hydride will form a primary. They will never form a secondary alcohol. They will form a primary alcohol. With sodium borohydride, they have no reaction because sodium borohydride cannot react again. This is why the reaction does not happen to start with. With acid chloride, same thing. Chlorine is going to be the leaving group. So with esters, the OR is the leaving group. With acid chloride, chlorine is the leaving group. But if you are working with sodium borohydride, there will be no reaction with both. Let's have an example for acid chloride and lithium aluminum hydride. Same idea. Hydride attacks, form a negative charge on the oxygen. This closes and the chlorine is going to leave. Chlorine is a good leaving group in this case. And then the hydride is going to attack again, form a negative charge, and then you do the protonation and your product is always a primary alcohol. The mechanism you are responsible for. There are extra problems in the problem sets. Please work those out.